Welcome to Lecture 17 for ME 149, Introduction to Analytical Target Cascading. Engineering system design is usually performed by a number of coordinated design groups. The design of modern engineering systems are too complicated for a single engineer or even a single design group to manage. Early in the development process, system requirements are set based on customer needs and market requirements. For example, if a design organization is designing a car, it might set requirements for performance, safety, reliability, comfort, user convenience, environmental impact, or for meeting government regulations. Requirements set at the beginning of the development process usually relate to system-level behavior. But like other system design efforts, the design is performed by distributed design teams, and each design team needs to know what these system-level requirements mean for their particular subsystem that they are responsible for developing. In vehicle design, there are separate organizations responsible for major vehicle systems, such as powertrain and structural design. Within these organizations are groups responsible for developing subsystems that are a part of these vehicle systems. For example, within the powertrain design organization are groups developing the engine and transmission subsystems. While this is a simplification of actual design organizations, hierarchical organizational structures like this are common. When we represent design organizations using hierarchical diagrams, it's helpful to define some terminology here for describing the structure. Here, powertrain is the parent subsystem of the engine and transmission subsystems, while powertrain is a child element of the vehicle subsystem. Here, we use the term target to represent system requirements that are numerical, such as fuel economy or acceleration performance. It's important to keep in mind that in systems engineering, requirements are often textual, and the process of setting numerical system targets based on textual requirements is by itself an important step in the system development process. We want to be able to take the top-level system targets and figure out targets for subsystems in the hierarchy such that the resulting system design will meet the top-level targets. This is an iterative process known as target cascading. Different design organizations have different levels of formalism and how they go about target cascading. The basic idea is that targets are propagated down in the hierarchy, and each design group in the hierarchy does their best to match these targets. Targets need to be set for each subsystem that correspond to metrics that describe subsystem behavior. For example, the powertrain system design group may specify a target power loss curve for the engine design group. The actual power loss curve that the engine design group can achieve using available technology and resources is the response to this target. Ideally, responses match their corresponding targets. If they don't, the system is inconsistent. Why might this be the case? Why might it be impossible for a design group to meet its targets? It would certainly simplify the system design process if targets could always be met. First, a target might be physically impossible to achieve with the current laws of physics or available materials or technology. A subsystem design might have local design constraints that make it impossible to achieve targets. For example, it might be impossible to design a suspension spring with the high stiffness rate that simultaneously fits within the available space for the suspension and has good reliability. Targets might also not be met because a design group does not have sufficient time or resources to meet them, or because the budget for that subsystem does not allow materials or technologies that would enable meeting the targets. What can we do if subsystem targets cannot be met on the first try? What's the next step? Often subsystem design problems, including the top-level design problem, can meet their targets in more than one way. In other words, there's some degrees of freedom and how subsystem design targets are met. Suppose subsystem I has some flexibility in how it meets targets Ti. In other words, there are some degrees of freedom in how the targets are matched. If in the first attempt at target cascading, subsystem I is able to meet its targets, but sets targets for its child subsystem J that cannot be met, perhaps subsystem I could meet its targets in a different way that involves a new set of targets for subsystem J that are achievable. To make this more concrete, suppose subsystem I represents a vehicle suspension, and subsystem J represents a suspension spring, which is just one of the many child subsystems that feed into this suspension subsystem. If the suspension performance targets can be met with a particular suspension design configuration that requires suspension spring properties that are physically impossible to achieve, perhaps a different suspension design configuration could be used that meets the suspension design targets that will work with a suspension spring that is feasible to manufacture. This iterative coordination between parent and child subsystems is really a negotiation process. This negotiation process needs to take place throughout the system, wherever initial targets cannot be met. To be successful in target cascading, we need some type of iterative coordination process to find a set of subsystem targets that works for the whole system. The degree of formalism this process has varies between organizations. It might be some ad hoc interactive coordination process that has evolved over time in a company, or perhaps it's a codified process as in formal systems engineering. In any case, these iterative loops are a very expensive aspect of the system design process, particularly if these iterations involve manual design exploration and physical prototyping and testing. Any technique that could reduce these loops, these iterative loops, would be especially valuable. The expense of developing engineering systems is becoming an issue of increasing importance. The complexity of modern engineering systems is rising, but the conventional processes that have been in place for decades and are still largely being used to design these systems do not scale well. The presence of nested iterative loops result in development efforts that increase nonlinearly with system complexity. In other words, the development effort is not proportional to system complexity. It increases faster than proportional to system complexity. Let's have a look at the problem facing an individual subsystem design group during the target cascading process. This group needs to develop a subsystem design that comes as close as possible to meeting subsystem targets, while staying within subsystem budget and design restrictions. What does this sound like? This sounds an awful lot like an optimization problem. What if we could develop a computational model for this subsystem being designed, and then use optimization within the target cascading process? This is the essence of analytical target cascading, or also known as ATC. This is an analytical approach to target cascading. ATC is a model-based methodology that uses models or simulations of subsystems in conjunction with optimization and a coordination algorithm for the overall system design problem. An optimization subproblem is formed for each subsystem design problem. And each optimization problem is responsible to find a subsystem design that matches its targets as closely as possible while staying within local subsystem design constraints. A coordination algorithm is used to guide the solution of these optimization subproblems such that they converge on a set of targets that is consistent across the whole system. Here's another view of what ATC does. We provide the ATC process with a set of top-level system targets, T1 in this figure. And The main output of the ATC process is a set of consistent subsystem targets. How can these subsystem targets be used in a broader system development process? Since ATC is based on approximate models, the output of ATC is not a final system design. Rather, these targets can then be used as a good starting point for the subsystem design teams. Good starting points can help reduce the number of expensive iterations in the human design organization required to develop a consistent system that meets top-level requirements. When ATC was first developed, the ability to provide high-quality targets for subsystems and help reduce system development time was seen as its primary value. ATC applies to systems that are decomposed using a hierarchical approach. ATC was motivated by system development processes and is similar conceptually to processes that involve human engineers. It is important, however, to make the distinction that the ATC solution process itself involves only computational models and decisions made via optimization. The results of the AT solution process can be used in the broader system development process. Here we see the hierarchical analysis structure of a system that can be used with ATC. The X's are design variables that are input to each subsystem, and the Y's are coupling variables, that is, analysis outputs that are required as inputs to other subsystem analysis functions. In this diagram, all of the coupling variables flow up. Early ATC implementations applied only to problems with this analysis structure. But there's no reason why ATC cannot handle systems with coupling variables that flow down in the hierarchy. The diagram of the powertrain design problem has a similar structure. For example, the top-level powertrain simulation requires as input a characterization of subsystem properties such as engine power loss maps. These power loss maps are coupling variables. As we saw a moment ago, the ATC process can be viewed as a function where top-level targets, T1, are inputs, and a consistent set of subsystem targets are the output. The resulting targets can then be used by engineers in their system development efforts. Engineers can proceed with some confidence with these targets that if they can develop designs that meet these subsystem targets, the resulting system design will also meet top-level targets. The targets produced by ATC are only as good as the underlying system model. It is especially important to capture system interactions accurately during modeling. Because ATC operates on an approximate model, the targets are valid only with respect to the model. So some iteration in the design organization will be required after the ATC process. If the expense of these iterations, the manual iterations, is reduced by using ATC targets, then there's definitely value in applying ATC to the system development process. What if the ATC process is unsuccessful? That is, what if we cannot arrive at a set of subsystem targets that enable us to meet top-level targets? This might be because the top-level targets are just physically impossible to meet. While the ATC process might not have identified suitable targets for the subsystems, it still provides a rich set of information that can help us identify how to move forward. For example, we might consider adjusting one of the targets to make the target cascading process feasible, or problem feasible. ATC provides sensitivity information for each target that can help us decide what modification would make the biggest difference. It can also guide us in other modifications to the target cascading problem, such as modification of local subsystem constraints or decisions about what aspects of the subsystem model to improve. This diagram provides some context for how ATC may be incorporated into the broader system development process. At the left, we provide the top-level targets to the ATC process, which then outputs a set of subsystem targets. Design groups then work concurrently to develop systems that meet these targets, with the idea that if the targets are met, the interactions between subsystems will have been accounted for, and the result will be a consistent system that meets top-level targets. Because ATC is based on approximate models, the actual system design may not meet top-level targets. This is checked during a system validation step, where engineers determine if the combined system design is feasible, consistent, and meets system targets. If this is not the case, if the validation step fails, the process then needs to be repeated with an improved ATC model. Results from the last ATC solution, combined with experience from subsystem embodiment design and system validation, can inform modifications to the ATC model. For example, if some important constraints were overlooked in the ATC model, they might be identified during one of the subsystem designs. Specific aspects of the system model might not be accurate enough, and validation and ATC solution results can help us zoom in on what parts of the model need to be improved. During embodiment design, we might identify a design constraint that was overlooked in the ATC formulation. If validation fails, the top-level targets might simply be infeasible and either need to be adjusted, or perhaps some design constraints could be relaxed. Sensitivity information from the ATC solution can tell us which target or constraint modifications would have the most impact. ATC has the paradoxical property of being a reductionist approach that produces holistic system designs. In the embodiment design phase, each of the subsystem designs can be performed relatively independently, yet when the subsystem designs are merged, the result is a well-integrated system design. This is because ATC accounts for interactions between subsystems when generating subsystem targets. This is accomplished through a combination of penalty functions and subproblems that enforce consistency, and a coordination algorithm that guides the repeated solution of optimization subproblems toward a consistent and optimal system design. A stretch target is a target that is intentionally set too high or low to actually be achieved. Stretch targets are useful in design to help explore what is physically possible. If we set a stretch target and apply ATC, the target will not be met, but the result is useful. We will know what the limit of our system is. For example, in designing a passenger car, we might set 100 miles per gallon as a fuel economy target, but after the ATC process achieve only 40 miles per gallon. Using only stretch targets at the top level, in essence, converts a target cascading problem into a system design optimization problem. In other words, ATC is not just a tool for target cascading, but for engineering system design optimization as well. Now let's have a look at the details of implementing ATC. We'll start with a quadratic program as a simple example to demonstrate how to formulate and solve an optimization problem using ATC. Here is the all-in-one, or MDF, formulation of the example problem. We want to minimize the objective function a1 with respect to the two design variables x1 and x2, subject to a linear constraint, g1. All the parameters for the problem are defined below. Here we are using a stretch target for a1 of 0. For simplicity in the formulation, we've dropped the target of 0. This is mathematically equivalent to retaining the target in the formulation. The solution to this problem using ATC has been implemented in MATLAB and can be downloaded from the MATLAB Central File Exchange. This example is File Exchange submission number 25390. Let's have a look at the analysis structure for this problem. This step is helpful for deciding on a system partition. It helps us understand any interactions that might arise from partitioning the system into subproblems. Here we have two analysis functions. A1 is the objective function. A2 is part of the constraint, G1, but also outputs the coupling variable, y12. That is the quantity output by A2 that is required as input by A1. In this case, there are only two partitions possible. We solve it as a single we can solve it as a single subproblem, but that is just the all-in-one problem, so it's not very interesting to us right now. The other option is to split the system into two subproblems. Here, subproblem 1 is the top-level problem in the system hierarchy, and subproblem 2 is the bottom-level problem. We don't have any shared design variables. x1 is a local variable for P1, and x2 is a local variable for P2, problem 2. The partition cuts across the analysis coupling relationship between A1 and A2. We need to be able to solve each of these subproblems independently during the ATC coordination process, but somehow need to account for this analysis interaction. The way we can do this is by creating an independent copy of the coupling variable y12 in subproblem 1. We use a superscript 1 in parentheses to indicate that this copy of y12 is the one associated with subproblem 1. In subproblem 2, the output of A2 is the copy of y12 associated with subproblem 2. Looping back to the purpose of ATC, we can describe the meaning of these two variable copies. The copy in subproblem 1 is the target for the copy in subproblem 2, and the copy in subproblem 2 is the response. In creating these coupling variable copies, we have made the two subproblems independent. They could be solved in parallel, but this has broken the coupling relationship between A1 and A2. Solving these two subproblems in parallel will not give us the same solution as the original optimization problem. This is a simple quantitative description of what happens when designers of engineering systems partition the design problem into subproblems, but fail to account for system interactions. The resulting design may have optimal subproblems, but the overall system is not optimal. It is not equivalent to solving the system design problem using a holistic all-in-one approach. ATC lets us have it both ways. It allows us to partition our system into independent design problems, but still account for interactions and deliver a system optimal design. So how exactly can we ensure that our system designs are consistent? How can we ensure that coupling variable copies in different subproblems agree with each other? One obvious answer is to create a new constraint that requires coupling variable copies to match. Here is the consistency constraint for y12. If it is satisfied, that is, if it equals 0, the two copies match. That is, they are consistent. Notice that we can replace the copy from subproblem 2 with A2, since y12 is the output of A2. We might be tempted to simply include this consistency constraint in each of the subproblems. In practice, this does not work so well. Often, when we are far from the final system optimal solution, it is impossible to satisfy the consistency constraint because of the other constraints and requirements in subproblems. In other words, the optimization subproblems are infeasible because of these additional equality constraints. There are other numerical problems also associated with using equality constraints directly in optimization subproblems. An effective solution to this issue is to relax the consistency constraint using a penalty function. The equality constraint is replaced with a penalty function that is added to the objective function. This helps ensure the feasibility of individual subproblems. Equality constraints may not provide enough flexibility in optimization subproblems, especially if we are far from the solution to the system design problem. If equality constraints were used instead of a penalty function and caused even a single subproblem to be infeasible, the ATC solution process would fail. Consistency constraint relaxation is essential to the success of ATC solutions. Here are the ATC subproblem formulations for this optimization problem. Phi1 and Phi2 are the penalty functions that help enforce consistency in the subproblems. In early ATC formulations, a simple quadratic penalty function was used. You might remember that there are some problems with using quadratic penalty functions. In order to satisfy the original equality constraints exactly, the quadratic penalty weights would need to be infinite, which clearly is not practical. If we use penalty weights large enough to ensure reasonable accuracy, the optimization subproblems become ill-conditioned and are very difficult to solve. A second generation of ATC formulations was developed in 2005 that replaces the quadratic penalty function with an augmented Lagrangian penalty function. This makes it possible to satisfy constraints exactly without requiring infinite quadratic penalty weights. This new formulation makes these subproblems easier to solve and has brought down the computational expense of solving ATC problems by up to 2 orders of magnitude. I should point out that both versions of ATC have proven convergence properties, something that is actually not common for decomposition-based design optimization methods. Let's go through each of these subproblem formulations. In subproblem 1, we are minimizing the original objective function plus an augmented Lagrangian penalty function that penalizes violation of the consistency constraint C1. In other words, the penalty function phi1 keeps y12 superscript 1 from deviating too far from the known achievable value of y12 superscript 2, which is an output of subproblem 2. Both phi1 and C1 are defined below the optimization problem. Phi1 is the augmented Lagrangian penalty function that has a linear term in addition to the quadratic term. V1 is the linear penalty weight, and W1 is the quadratic penalty weight. During the course of solving subproblem 1, V1 and W1 are held fixed. During the ATC coordination process, each subproblem will be solved multiple times, and in between subproblem solutions, the penalty weight values are updated. In a few moments, we will go through the details of the coordination algorithm. With this system partition, subproblem 1 has no local design constraints. It is an unconstrained optimization problem, so it can be solved with an algorithm like Newton's method. In fact, since the objective function is quadratic, an analytical solution to subproblem 1 can be derived by setting the gradient of the objective equal to 0 and solving for x1 and y12 superscript 1. We can think of the copy of y12 in subproblem 1 as the target for the output of analysis function 2 located in subproblem 2, and the copy of y12 in subproblem 2, which is the output of A2, as the response corresponding to this target. At ATC convergence, we would like the target and response to match, or in other words, we would like the consistency constraint to be satisfied. In subproblem 1, y12 is an independent optimization variable, so the optimization algorithm is free to choose a target value that produces the best system performance. The penalty function is in a way a reality check. It keeps the target from deviating too far from values that can actually be achieved by subproblem 2. Subproblem 2 is responsible for coming up with a subsystem design that comes as close as possible to matching its performance target. Looking at subproblem 2, we have no local design objective function, so the only part of this subproblem's objective function is the augmented Lagrangian penalty function. Consequently, the sole purpose of subproblem 2 in this simple example is to find a subproblem design defined by x2 that comes as close as possible to matching the subproblem performance target while satisfying the local design constraint G1. Unlike subproblem 1, this is a constrained optimization problem and can be solved using an algorithm for nonlinear programming such as SQP. Because it has a quadratic objective and a linear constraint, it is actually a quadratic program and could be solved using more specialized quadratic programming techniques. Notice that the penalty function weights are unique for each subproblem. That is, V1 and W1 do not necessarily match V2 and W2 during the ATC solution process. There are subtle differences between the penalty functions and consistency constraints in each subproblem. In subproblem 1, y12 superscript 1 is independent, and y12 superscript 2 is a fixed parameter. And in subproblem 2, the converse is true. At ATC convergence, the linear penalty weights are equal to the Lagrange multipliers for the corresponding consistency constraints. These values give us insight into the nature of each consistency constraint, as Lagrange multipliers are a measure of problem sensitivity with respect to optimization constraints. Solving each subproblem just once will not produce a consistent and system-optimal design. As you might remember, during the section on penalty and barrier functions, the augmented Lagrangian penalty method requires that a sequence of optimization problems is solved, where each solution has updated penalty weights based on the last solution. This is the core of the ATC coordination algorithm. The main difference here from what you saw earlier in the section on penalty and barrier functions is that instead of solving just a single optimization problem multiple times, here we need to solve a whole set of optimization problems multiple times. Here is a simple version of the ATC coordination algorithm for a system with two subproblems. K is the iteration number for the outer loop of the coordination algorithm. We start by initializing the penalty weights. While there exist some sophisticated methods for choosing initial weights, here we will just set the linear weights to 0 and the quadratic weights to 1. Keep in mind that proper problem scaling is essential here. You will run into numerical troubles if coupling variables differ by orders of magnitude. In this version of the ATC coordination algorithm, we will solve the subproblems in sequence. First subproblem 1, and then subproblem 2. Recall that subproblem 1 requires y12 superscript 2 as an input, which is calculated by subproblem 2. Since we haven't solved subproblem 2 yet when we're starting the ATC process, we need to choose a reasonable initial guess for y12 superscript 2 so we can solve subproblem 1. This initial guess needs to reflect a realistic value, as it will influence the target set by subproblem 1. With all the quantities initialized, now we can solve subproblem 1. Then we take the resulting value of y12 superscript 1 and pass it to subproblem 2 as a fixed target value. Next we solve subproblem 2 and save the value of y12 superscript 2 to use in solving subproblem 1 during the next iteration. Before proceeding with the next iteration, we check to see if convergence conditions have been met. Common convergence tests include checking whether consistency constraints are close to 0 within some tolerance, and that the change in coupling variable values is small between iterations. If the coordination algorithm has not converged, then we update the penalty weights in step 4 using the method of multipliers. These update formulas are vector equations. V and W are the vectors of all penalty weights in the system, and C is the vector of all consistency constraint outputs. The new value of V depends on the current value of V, W, and C. The open circle in this formula depicts the Hadamard product, an element-by-element multiplication of the vectors. In MATLAB syntax, this is the same as the dot times operator. W is updated with a simple multiplier beta, that is, some value greater than 1. The choice of beta has a significant impact on the performance of an ATC algorithm. Large beta values place greater emphasis on consistency, but can make subproblems ill-conditioned and can result in small steps and slow progress. Small beta values, on the other hand, make the solution process more flexible and allow larger steps, but the coordination process may take more iterations to converge to a consistent solution. Studies have been done to explore values of beta that work best, but the choice of beta depends on the specific variant of the ATC coordination algorithm that you're using, as well as the system design problem and the system partition. I should point out that it is essential that each subproblem needs to be ATC subproblem needs to be solved reliably. If a single subproblem fails to solve correctly, it may either cause the ATC solution process to fail entirely or, at minimum, invalidate the results. This highlights the need for engineers who are developing ATC implementations to have a solid understanding of design optimization fundamentals. This coordination algorithm can be viewed as a negotiation process in a design organization. The top-level design group sets a target for subsystem design teams based on what would be best for the system, as well as what they understand about the capabilities of subsystem design teams. The subsystem design teams then do their best to meet these targets and report back to the top-level design team. If the results don't match the targets, the top-level team takes this information into account when deciding on new targets that they think might be achievable for the subsystem design teams. This process repeats until the top and bottom level design teams agree on a set of achievable targets. Let's have a look at an actual MATLAB implementation of the ATC solution to this example problem that we just looked at. This code is available, as I said, on the MATLAB file exchange. Let's have a look at an actual MATLAB implementation of the ATC solution to this example problem. This code is available on the MATLAB Central File Exchange. The all-in-one and ATC problem formulations are given in the comments. First, for comparison, we solve the all-in-one problem, also known as MDF, using fmin_con, the MATLAB function for constrained optimization. The objective and constraint functions for this problem are defined below. Next, we solve the ATC implementation of this example problem. First, we initialize the penalty weights. Beta, coupling variable, and consistency constraints. Here the coupling variable is denoted using Z. The while loop is the outer loop of the ATC coordination algorithm. It repeats until either termination conditions are met or the maximum number of iterations is exceeded. The first step in the outer loop is to solve the inner loop problem. In this simple example, the inner loop consists only of solving the subproblems in sequence once. We then use the inner loop results to update the penalty weights. Here's the implementation of the inner loop. Subproblem 1 is solved, and then subproblem 2. Each subproblem solution is implemented in its own function. Subproblem 1 is solved using fmin_unc, since it is an unconstrained optimization problem, and subproblem 2 is solved using fmin_con, since it is a constrained optimization problem. Notice that V, W, and Z are passed into the optimization algorithms as fixed parameters. Each subproblem objective function is implemented below. Notice the augmented Lagrangian penalty function defined in each. Here's the penalty function for the objective in subproblem 1, and here's the penalty function for the objective function in subproblem 2. Let's run the code and compare the all-in-one results with the ATC results. It's already completed. In just 3 outer loop iterations, ATC converged to the same solution as the all-in-one problem. We can see that both the design vector and the objective function values are identical. Let's have a look at a more general formulation for ATC. Here's the optimization problem for a general subproblem in an ATC hierarchy. This is the formulation for subproblem I. This formulation accounts for all of the features in the previous example, as well as some features we haven't seen yet, such as how ATC manages shared design variables. ATC allows for system design problems with a local objective function for each subproblem, f subscript I. As an ATC formulation that has more than one subproblem with a local objective is mathematically equivalent to an all-in-one problem where the objective function is the sum of all the local objective functions. In addition to the local objective function, the optimization subproblem seeks to minimize the deviation between responses and targets using a penalty function. In other words, the penalty function has the responsibility to drive the system toward a state of consistency. Here we assume an augmented Lagrangian penalty function is used. In this case, phi depends also on penalty weights vi and wi. The ATC subproblem has several different optimization variables. X bar I is the set of all design variables that are required as input to the analysis functions in subproblem I. Keep in mind that some of these design variables might be shared with other subproblems, and some might be local variables, that is, design variables that are only used in this subproblem. The shared design variables here are local copies that must match the corresponding local copies in other subproblems at convergence. Y bar I are the local copies of coupling variables required as input to subproblem I. These independent variables are targets that subproblem I sets for other subproblems that its analysis functions are linked to. The structure of an ATC problem must be hierarchical. Often relationships in engineering design problems are hierarchical and fit nicely with ATC solutions. However, many engineering design problems do have non-hierarchical relationships in their analysis structures. It is still possible to solve many of these system design problems using ATC. For example, if two child subproblems share a variable or have a coupling variable pass between them, these relationships can be managed by a common parent subproblem. This is why we have the other two types of optimization variables. Y bar Ci are the coupling variables passed between child subproblems, and X bar Sci are the design variables shared between child subproblems. The consistency constraint Ci is driven to 0 by the penalty function. Ci quantifies the consistency of shared and coupling variables, both between subproblem I and other subproblems, and also between child subproblems of subproblem I. Let's go through another ATC example with a little more complexity. Recall the vane airflow sensor problem from earlier lectures. It has feedback coupling between aerodynamic and structural analyses. The sensor deflection theta depends on the drag force F, but because of the changing frontal area, the drag force depends on sensor deflection. So this forms a feedback coupling relationship. Let's have a look at the undecomposed optimization problem. Here's the all-in-one optimization formulation, also known as MDF. Given a particular airspeed v through the sensor, we want the sensor deflection to be as close as possible to a target deflection, theta hat. This is a sensor calibration problem where we are using a least squares approach to get as close as we can to the desired sensor output. Now let's have a look at the ATC formulation where we have applied a disciplinary partition. In this partition, subproblem 1 includes the structural analysis, and subproblem 2 involves the aerodynamic analysis. Within this partition, the vane length L is a shared design variable, and theta and F are coupling variables. In subproblem 1, we seek to minimize the system objective function along with augmented Lagrangian penalty function. There are two optimization variables. L superscript 1 is a local copy of a shared design variable, and F superscript 1 is a local copy of a coupling variable. Here we include the drag force constraint as a local design constraint in subproblem 1. The consistency constraint, C1, requires consistency between the shared design variable and the two coupling variables. Notice that C1 is a function only of L superscript 1 and F superscript 1. Theta superscript 1, the sensor deflection, is the output of the structural analysis function, which is a function of L superscript 1 and F superscript 1. In subproblem 1, the quantities theta superscript 2, F superscript 2, and L superscript 2 are fixed parameters determined by subproblem 2. Let's have a look at subproblem 2. Here the objective is to minimize the penalty on inconsistency measured by C2. The terms of C2 are identical to C1, but notice that the functions are different. They depend on different variables. Here we have three optimization variables. L superscript 2 is a shared design variable. W superscript 2 is a local design variable, and theta superscript 2 is a local copy of a coupling variable. It can be viewed as the target that subproblem 2 is setting for the output of the structural analysis. The consistency constraint, C2, depends on these same three optimization variables. F superscript 2 is the drag force computed by the aerodynamic analysis, and it depends on all three optimization variables. Theta superscript 1, F superscript 1, and L superscript 1 are all fixed parameters in subproblem 2 and are determined by the optimization problem in subproblem 1. F superscript 1 can be viewed as the target drag force set by subproblem 1 for subproblem 2, and F superscript 2 is a corresponding response that can actually be achieved. Subproblem 2 also includes the area constraint. Location of design constraints is somewhat arbitrary in an ATC formulation. In this problem, both design constraints could have been placed in subproblem 2. Where you choose to place design constraints may change the complexity of shared and coupling variable relationships in an ATC implementation. Often it is helpful to locate design constraints in subproblems such that the number or complexity of interactions between subproblems is minimized. Before we move on to the next example, I'd like to introduce an important term, linking variables. Shared design variables and coupling variables describe two different types of interactions between subsystems. Both of these types of variables are part of a larger classification of variables that we call linking variables. A linking variable links subproblems together, whether it is a design interaction or an analysis interaction. Linking variables are how we quantify system interactions in decomposition-based design optimization. Let's have a brief look at another system design example. In the past, we have discussed several types of system partitioning, such as disciplinary, physical component, or process partitioning. In product family design, instead of splitting up a single system design problem into subproblems, we define a subproblem for each system design in a family of product variants. Each product, or variant, in a product family has some common design elements with other variants in the product family. This commonality can reduce manufacturing, maintenance, and other product lifecycle costs. Each variant does have something unique about it that makes it more suitable for a specific application. While commonality in a product family can reduce costs, commonality also restricts us from optimizing each product for the best possible performance in its intended application. How many design elements you choose to be common between product variants will impact this trade-off between cost reduction and specialized performance benefits. If we use ATC to solve a product family design problem, commonality can be quantified using shared design variables. For example, if we are designing two aircraft that share a common fuselage but can have different wing designs, the design variables pertaining to the fuselage are shared design variables. That is, they must be equal between the two aircraft. If we want to change the level of commonality in the product family, we just need to change what design variables are shared. The structure of ATC is a natural fit for product family design. In this example, we want to develop two aircraft, each for a different mission, but we want to minimize the total operating cost for the whole fleet. Here, the main wing design is the common design element, but other design elements can be varied independently. The top-level design problem involves a cost analysis for a fleet consisting of these two different types of aircraft. Subproblem 1 is this top-level design problem. Subproblem 2 is the design problem for aircraft A, and subproblem 3 is the design problem for aircraft B. The subproblem for aircraft B is not shown since its formulation is very similar to subproblem 2. Using this product family design problem, an investigation of how ATC performance varied with different values of the beta parameter for penalty weight updates was performed. Here, the horizontal axis shows the number of ATC outer loop iterations, and the vertical axis in this plot is a metric for overall system consistency, that is, how well responses match their corresponding targets. Here we can see that a beta value of about 1.3 provides a good combination of system consistency in relatively few ATC outer loop iterations. Before we end, it's important to take a moment to discuss how ATC relates to multidisciplinary design optimization methods, or MDO methods. While ATC and some MDO formulations are mathematically similar, they were developed for completely different reasons. ATC was motivated specifically by the need to identify high-quality targets for subsystems with the objective of reducing manual design iterations. It was inspired by heuristic target cascading processes used in industry and was developed to be a mathematically rigorous alternative to manual target cascading. MDO was primarily developed by researchers in the aerospace industry seeking ways to account for disciplinary coupling in their system design efforts. ATC can be extended to solve MDO problems and has nice provable convergence properties, something that many multi-level MDO formulations lack. Both ATC and MDO formulations are considered to be methods for decomposition-based design optimization. In closing, I'd like to highlight some motivations for considering using a decomposition-based design optimization approach, such as ATC. First, reductionist approaches that still account for interactions make it possible to tackle increasingly difficult engineering system design problems. Often, these problems have a sparse structure, and intelligent system partitioning methods can exploit this sparsity in a way that leads to very efficient system design solution approaches. Methods like ATC are parallel by nature. Optimization subproblems are temporarily independent in the ATC solution process and can be solved using coarse-grained parallel computing. Often, disparate design groups own the different analysis tools for a system design problem, and decomposition-based approaches are congruent with this distributed ownership model in an organization. Finally, it is often the case that specific disciplines have specialized design optimization techniques, such as optimal control or structural optimization. The specialized optimization techniques can be leveraged in a decomposition-based design optimization approach. With this summary, I will conclude this lecture introducing analytical target cascading. Thank you.